We saw in the last couple of videos how with a little bit of catalytic acid or base, you can turn the alpha carbon into a nucleophile. And so we'll see acid or base in the first steps of almost all the reactions in this chapter. And we see it here. We have this H3O plus in brackets in the very first step. That's catalytic acid. That's going to turn that alpha carbon into a nucleophile. And so let's draw out the mechanism for this first one. We'll actually draw out the mechanisms for all of them because the question is asking you both to predict the major product and to propose a mechanism for its formation. But in this first one, let's just think through the mechanism, and then we'll see if we can use what we learn to predict the products in the future ones, and then justify those through their mechanisms. So in this case, we'd have this ketone, and now after those last few videos, when you see this, you don't just want to see the ketone, you also want to see the enol, where this alpha carbon can become nucleophilic. Now if you treat this with catalytic acid, then the mechanism will at first be exactly like the mechanisms that we drew and explained in detail in those previous videos. Excuse me. The slightly negative oxygen here sticks to and steals one of the slightly positive hydrogens in hydronium. The electrons that were keeping the hydrogen there snap back onto the oxygen. And so that's our first of our two proton transfers when you're doing this keto-enol tautomerism, as we presented in those previous videos. So when you get that, you now have that same carbon chain. The oxygen now has 3 bonds, and therefore a full positive charge. And you'll remember from the videos where we first walked through acid-catalyzed keto-enol tautomerism that at this step we have a resonance structure that becomes really significant. We have a pi bond between 2 atoms of differing electronegativity. That's one of the 5 resonance patterns. So you draw these brackets that warn people the true structure never looks like anything inside these brackets. It only always looks like the average of all of them. And you remind them to take the average with that special resonance arrow, which is different from an equilibrium arrow. Equilibrium means this molecule exists, it turns into this other molecule, and then turns back. That's equilibrium. Resonance means neither of these molecules exist, only the average ever exists. So when you have this resonance pattern, a pi bond between 2 atoms of differing electronegativity, to get the other resonance structure, you take the pi electrons and move them onto the more electronegative atom. And you can see why this would be this resonance is now significant, because the other resonance structure acts to stabilize this positive charge. The only thing is, so if those pi electrons go onto that oxygen, the oxygen no longer has a positive charge. The only thing is that now the carbon is missing those electrons, and so it has a full positive charge. So that's our resonance structure. From the first step, we also have water. So H3O plus lost the H plus, and water is left. And to get the enol, this water acts as a base. So this is acid catalyzed. The acid, the hydronium, gets used at first, but then it gets reformed. And this is where the alpha carbon comes in. You have that alpha hydrogen that is acidic. This base can steal that, and the electrons can move over to fill in the void where the positive charge is. Those electrons are attracted to that positive charge, so they create a pi bond there. And this is our second proton transfer. Whenever you go from the ketone to the enol, you always have 2 proton transfers. So the structure you end up with there is an enol. So you have the alkene and the alcohol. Alkene, alcohol, this is our enol. And this is significant because now these pi electrons can act as a nucleophile. So that's the mechanism for what happens just when you add the catalytic H3O+. Now the other thing that's bouncing around in this solution with that first step is molecular bromine. The bond between the bromines is perfectly nonpolar covalent. Both of the bromines have this exact same electronegativity. So there's no reason why there would be a slight charge on either of these bromines. But as the bromine moves close to the pi bond, as it's bouncing around in the solution, it moves close to the pi bond, and the electrons in the pi bond repel the electrons in this bromine atom. The bromine is a big atom, so the electrons have plenty of space on the opposite side of the atom to sort of collect. And there are fewer electrons toward the pi bond, and so you sort of induce this dipole in this one atom. And so now there's an electrophile on the bromine. So the charge of the electrons in the pi bond made all the electrons in the bromine flee. Now there's a slight positive charge on that side, and so this can attack the bromine as a nucleophile and kick the other bromine off as a leaving group. And this should seem really familiar from Organic Chemistry 1. And when you first learned about addition reactions to alkenes, you learned about halogenation or bromination, where you add Br2 to an alkene. Well, that's exactly what we're doing here. And the first step was exactly what we're doing here. So this is nucleophilic attack. You may also think of this as loss of a leaving group. Okay, well, this will add the bromine on the alpha position and the other carbon will have a positive charge. To some extent, the lone pairs in the bromine will sort of donate some electron density here, and it'll form a bromonium ion. If you remember from Organic Chemistry 1, but that's not a big deal. That's not something you'd have to worry about here. There's one other thing, and actually it may even be a more correct way of drawing what happens, because in addition to this pi bond acting as a nucleophile, it will often get a push, and we've seen these other pi electrons, or these lone pairs, form a pi bond to give electrons a push before. So if these leave, instead of this full charge forming, these electrons can come down at the same time and sort of balance that by giving a pi bond there. So now the oxygen has a full positive charge, but the carbon doesn't. So it sort of gives these electrons a push. Now, I was going to draw that in 2 steps, but I think it's more correct to draw it all in 1 step, happening at once. So these lone pairs push down. That helps these electrons leave this carbon and attack the bromine. Okay. And so, at that step, we have another water molecule come in and do one last proton transfer. Slightly negative oxygen steals this slightly positive hydrogen, and the electrons go onto the oxygen to stabilize the charge there. So, at that step, you would end up adding a bromine on the alpha position. Now that is alpha bromination, but you'll notice that all we did was use this first step. So in the first step, we've done alpha bromination. After the first step, you would have the same molecule, just a bromine on the alpha position. That's what we've accomplished in this mechanism so far. We have the same ketone, but with a bromine on the alpha position. The second step has pyridine, and pyridine is a base. Pyridine is sort of like benzene, but with a nitrogen as one of the 6 atoms. So you have alternating single and double bonds, it's aromatic. There's a lone pair, though, on the nitrogen that is not involved in aromaticity. And the role of this pyridine, again, sort of goes back to Organic Chemistry 1. Anytime you see a halogen, so chlorine, bromine, iodine, you should think of substitution and elimination reactions, because halogens are great leaving groups, and that's what you need in both substitution and elimination reactions. If you have a leaving group in a nucleophile, then you do substitution. If you have a leaving group in a base, which is what we have here, then you do elimination. And so this pyridine is going to act to eliminate the hydrogen next door to the leaving group. So this beta hydrogen. This lone pair will steal this hydrogen. The electrons will go toward the leaving group and kick the leaving group off. So that's an E2 mechanism. And if you feel unfamiliar with that, I would encourage you to go back and watch some of the videos I made for Organic Chemistry 1. I'd be happy to send those to you. But this is the second step, pyridine. Pyridine steals that beta hydrogen and does an elimination reaction so that you have an alpha-beta unsaturated aldehyde or ketone. So this is that final product there. So here we have a couple different curved arrow patterns. We have proton transfer and loss of a leaving group. And those are the two staples of an E2 reaction. So in the first step, we do ketoenol tautomerism. That turns the alpha carbon into a nucleophile. And then it can attack bromine and give you this alpha brominated compound. And then in the second step, that's just a base, and that does an elimination reaction. Gives you an alpha beta unsaturated ketone. So your final product for this one would be this here, and the mechanism is drawn out below. Okay, let's go through this whole process for a couple more ketones, just to build confidence, become a little more comfortable with it. In this one, first let's think from the perspective of synthesis. We saw that what this does is it adds a bromine on the alpha position. Now we have two alpha carbons here, and the reaction could happen at either of them, but the major product will be on the more substituted carbon. And that'll be because in the enol you have the more substituted alkene, and that's the more stable alkene, so it forms more often. So the bromine, in the first step, you're going to add the bromine to the alpha position, and it will add to the more substituted alpha position more often. Then in the second step, you do an elimination reaction. Pyridine is a base, and it will take one of the beta hydrogens and give you an alpha beta unsaturated ketone. So that is that reaction. That's the reaction from the perspective of synthesis. If you're just trying to predict the product of this, that would be the product of those two steps. But let's walk through the mechanism. That's something that they're asking for here. They say to propose a mechanism for these reactions. So first, we have our ketone, and we're treating it with catalytic acid. That catalytic acid is going to form the enol. So this oxygen here steals one of those slightly positive hydrogens. The electrons snap back down onto the oxygen and hydronium to stabilize the positive charge on it, and that's proton transfer. That's the first step in this ketoenol tautomerism. What that gives us is a molecule whose resonance structure becomes significant. So that oxygen now has a full positive charge because it has 3 bonds, and we have a pi bond between 2 atoms of differing electronegativity. So we have resonance. So we draw the 2 brackets to warn people. The true structure is neither of the structures inside. It's the average of the 2, and we draw the special resonance arrow between them with 1 line and 2 heads. To draw the other resonance structure, we draw the pi electrons going onto the more electronegative atom in the pi bond. So the other resonance structure would look like this. The water from the first step comes in. And this is where you have to decide which alpha carbon you're going to use. There are hydrogens on both alpha carbons. Let's think about what happens in each case. Let's imagine this happening in two different cases. Let's say that it steals this hydrogen here. So our base, our water, slightly negative oxygen there, steals that hydrogen. The electrons go toward the positive charge to form a pi bond. In that case, you form a pi bond that is tri-substituted. Notice that the carbons in these double bonds are bonded to 1, 2, 3 other carbons. These being bonded to other carbons means that the pi electrons in this pi bond can sort of slip out into one of the sp3 orbitals on those carbons. And so that helps the electron density spread out through what's called hyperconjugation. That's where the pi electrons, a p orbital, allows some electron density to leak out into an sp3 orbital that doesn't really align perfectly, but one of the lobes kind of do. So this would be like a neighboring carbon, and this would be one of the carbons in the pi bond. So because of hyperconjugation, that tri-substituted double bond is stabilized. Okay, now imagine the other scenario. Imagine that the water molecule had attacked the other alpha hydrogen, and the electrons went to the positive charge there. In that case, the pi bond would have formed on the other side. But notice that this is only di-substituted. You have only 2 carbons here, right? In the other one we had 1, 2, 3. So this is only di-substituted. So there are only 2 places where hyperconjugation can allow the electron density to spread out, whereas here there were 3 places where hyperconjugation would allow the electron density to spread out, because the electron density would spread out more here. That's more stable. The more substituted product is more stable, and so it's more likely to form. So you would technically get a mixture of both of those, but the major product would be where the base steals the alpha hydrogen on the more substituted carbon, and you get the pi bond, the more substituted pi bond. That's more stabilized because it has more hyperconjugation between the p orbitals in the pi bond and the sp3 orbitals on the carbons bonded to them. Okay, so that's the mechanism for this H3O+. That turns this sort of alpha carbon area into a nucleophile. We saw in the last example how if there's a bromine there, it can feel the negative charge in the pi bond. The electrons in the bromine would flee away from it. The side of the bromine facing it would become slightly positive, and with a little push from the electrons in the oxygen to stabilize the carbon as these leave, these pi electrons can attack that bromine and kick the other bromine off. So this is nucleophilic attack. And what we have after that step is a bromine on the alpha position but still a full positive charge on the oxygen. So water can come in, slightly negative charge on oxygen can steal this hydrogen, the electrons can go to stabilize the oxygen there, so this is just a proton transfer. And that gives us the bromine on the alpha position. And that was when we were thinking of this just from the perspective of synthesis, that's what we knew would happen based on that first step. That first step adds a bromine on the alpha carbon, and the more substituted alpha carbon. In the second step, you treat the molecule with pyridine. Pyridine is a base, and so it's going to do an elimination reaction. Pyridine is basically benzene, but where one of the atoms has been replaced by a nitrogen, one of the carbons. The nitrogen has a lone pair that's not involved in the aromaticity, so it can steal a beta hydrogen. This is a classic E2 mechanism. Steal that beta hydrogen, the electrons go toward the leaving group and kick the leaving group off. So you have a proton transfer, and you have loss of a leaving group, the two staples of an E2 reaction. And when you do that, you have an alpha-beta unsaturated ketone. Could also be an aldehyde, but it's called alpha-beta because the carbonyl carbon is the carbonyl carbon. The carbon next to it is the alpha carbon, and then the one after that is the beta carbon. And you have fewer hydrogens here than you possibly could. You could still hydrogenate this. You can add a hydrogen on each of those if you took the double bond away. So it's called unsaturated because it's not saturated with as many hydrogens as it possibly could be. And unsaturation is just a pi bond. Or a ring, as we saw when we did the degrees of unsaturation. So we have an alpha-beta unsaturated ketone in this case. And that's what we predicted when we thought of this reaction from the perspective of synthesis. But here you have that mechanism that you'll want to be able to draw. Okay, let's do the same thing for C. In this case, first let's think about this just from the perspective of synthesis, then we'll draw the mechanism. So just from the perspective of synthesis, we know that in this first step, we'll really just add a bromine onto the alpha position. The acid catalyst will create the enol. The pi bond in the enol will act as a nucleophile to attach a bromine. So after the first step, you'd have the bromine on the alpha position. The bromine is a great leaving group, so you can do substitution or elimination with it. If you treat it with a base, then you'll do elimination. If you treat it with a nucleophile, you do substitution. So if you treat it with a base, you do elimination, and so you'd get an alpha-beta unsaturated aldehyde in this case. So that's our prediction for what we would get in the product. But the question is still asking us for the mechanism. So we'll want to draw that for how this happens. So let's draw our original aldehyde, 2-methylpropanal, and we have the acid catalyst. So we want to show how with an acid catalyst we would turn this aldehyde into an enol. So the slightly negative oxygen in the aldehyde can attack one of the slightly positive hydrogens of hydronium, and the electrons would snap back onto the water. So we have a proton transfer. In general, when you do keto-enol tautomerism, it's just 2 proton transfers. So at that stage, or at this stage, we would have the same molecule just with a hydrogen attached where the oxygen is. And notice that oxygen has 3 bonds and so has a full positive charge. Now, there's a resonance pattern that becomes significant here because it helps to stabilize that positive charge, and that's when you have a pi bond between 2 atoms of differing electronegativity. When you have that, the pi bond goes onto the more electronegative atom. So because we have that resonance pattern, we drew the brackets that warned people that neither of the structures within the brackets is the true structure. The true structure is only the average of the two. We draw the special resonance arrow that tells people to take the average of the two molecules on either side, not to be confused with an equilibrium arrow. This resonance arrow does not mean that the structure is turning into this one and turning back. That's what the equilibrium arrow means. The resonance arrow means neither of these two structures ever exist, only the average ever exists. So the pi bond goes away and we form a new lone pair on the oxygen. At the same time, the carbon lost those electrons, so it now has a full positive charge. In the first step, hydronium lost an H+, so now it's just going to be water. And the water can act as a base. The alpha hydrogen is acidic. This water can steal that hydrogen, and the electrons can go toward the positive charge to create a bond, to stabilize it. So that's our second proton transfer. Whenever you do keto-enol tautomerism, you always have two proton transfers. So after that, you would have that molecule there. You would also recreate the hydronium, so you notice that it's a catalyst, because even though it is necessary to make the reaction happen, it doesn't get used up. You use it at first, but then it gets recreated, reproduced, so it's not like a reagent. A reagent is just used up and changed in the process of the reaction. A catalyst is used, but then reproduced, so it doesn't get used up in the overall in the course of the reaction. So now we have our enol, and the significance of that is that the pi bond there can act as a nucleophile. So if we look back at the recipe, the second thing we're adding is molecular bromine. And so this bromine can approach the negative charge, and as it gets close to it, the negative electrons in the pi bond repel the electrons in the bromine. Bromine is really big, so there's enough space for them to go on the opposite side of the atom. They flee the side that faces the pi bond, and so that side of the atom becomes slightly positive. With a little push from the lone pair above, these pi electrons are free to attack that slightly positive bromine and kick the other one off. So you have really nucleophilic attack here. You may think of this as loss of a leaving group. So at this stage, we have that new pi bond, and we have a bromine on the alpha carbon. The oxygen has 3 bonds and so has a full positive charge. So a water molecule can come in and steal that hydrogen. Slightly negative oxygen could steal the slightly positive hydrogen there. The electrons would snap back onto that oxygen, and we'd have our sort of first product, the result of the first step of our reaction. We have our original aldehyde just with a bromine on the alpha position. And that's what we predicted when we first thought about this from the perspective of synthesis. We said, when we do this first reaction, we'll add the bromine on the alpha position. Now, once you have a bromine there, you should think, okay, that's a great leaving group. What can I do with a leaving group? I could do substitution or elimination. If I treat this with a nucleophile could displace that, and you'd have substitution. If I treat it with a base, which is what pyridine is, then I would do an elimination and get a pi bond. So we can take this, treat it with pyridine. Pyridine is like benzene. It's a 6-membered aromatic ring. just one of the carbons is replaced by a nitrogen. The nitrogen has a lone pair on it, and that lone pair is not participating in the aromaticity, so it can act as a base. That lone pair can stick to a hydrogen. The electrons in the hydrogen can then go toward the leaving group and kick the leaving group off. So you have two things happening here. They're the staples of an E2 reaction that you learned about in Organic Chemistry 1, and that I have videos for if you're interested. There's a proton transfer and loss of a leaving group, both happening at the same time. And so what you end up with in this case is an alpha-beta unsaturated aldehyde. So remember, the carbon next to the carbonyl carbon is the alpha carbon, then the beta carbon. So it's alpha-beta unsaturated because you have a pi bond between the alpha and beta carbons. And that would be the product for that, that reaction. And so that's what we predicted also earlier above. So in this exercise, we drew the mechanism several times for first how you can, we combined the mechanism we learned last time for how an acid catalyst can turn a ketone into an enol, and how we used the significance of that, which is that it turns the alpha carbon into a nucleophile, and reacted it with an electrophile, a bromine molecule, and that put a bromine on the alpha position. And then we saw that once you have that bromine on that alpha position, that's really powerful because it opens up substitution and elimination reactions. And specifically in these exercises, we used elimination. The pyridine acted as a base, and so it stole the beta hydrogen, and that kicked the leaving group off. So we saw that that happens several times. We drew the mechanism out for it. One little detail you might remember is that when you do the alpha bromination, make sure the bromine goes on the more substituted carbon.